All right, hello world. I would say good morning because it is good morning to me, but based on the chat, I think I'm saying good afternoon to quite a few of our friends in the European area, and good evening to a few people as well. So welcome everyone from all over the world. We are going to get started with our webinar. Thank you so much for joining us. My name's Katie Sidwell with RTDS Technologies. I'm not going to speak for very long today. I'm really just introducing the company really briefly, and then I'm going to turn things over to my colleague Eric, and he will speak about our protection testing features, specifically our IEC 61850 features, and then we'll get a live demo, which should be really exciting. So let's get started. I encourage everyone to please submit questions via the Q&A panel throughout the webinar, and we will be answering those in real time, if you will. So if you're not familiar with the company RTDS Technologies, we're based in Winnipeg, Manitoba, which is a bit of a research hub for HVDC technology in Canada. And we pioneered real-time simulation for the power industry back in the 1980s by creating our technology, which is called the RTDS Simulator, or the Real-Time Digital Simulator. The original purpose of the technology was HVDC control testing, but the applications have expanded considerably, and now the technology is much more widespread, and a very large area of application is protection. Today we have over 75 employees, and we have a high level of control over this technology as our hardware and software developers, our power systems modeling team, after-sales support, and even our equipment assembly and quality assurance departments are all under one roof here in Winnipeg. We have users in over 50 countries. We basically have four main categories of user, and that's electric utilities, protection and control manufacturers, research institutions, and consultants. So all of the major manufacturers are users of the RTDS simulator. So this is just a few of the bigger names that are shown here. And these folks have really integrated hardware in the loop testing into the development of their protection equipment, including the rollout of IEC 61850 compliant units throughout the last several years. Recently, SEL, or Schweitzer Engineering Labs, has also factory tested their traveling wave-based protection with the simulator, and we'll touch on that a little bit later in the presentation. This is a look at a few of over 100 utilities around the world who are RTDS users. Protection testing is a big application for utilities, whether that is pre-commissioning for a digital substation, or wide area-based protection and control system with synchrophasers. So we're used quite a bit in this area as well. There are over 200 research and educational customers worldwide, so this is just a few shown here. There's quite a bit of protection research that's gone on. The University of Strathclyde, for example, have done a lot of work evaluating synchrophaser-based special protection systems. I know DTU in Denmark has done some work on distance protection performance in the presence of converters with different fault ride-through control strategies. If you're curious about more examples about any of this, we have a full list of technical publications online that are available. I just wanted to mention there are diverse opportunities to apply this technology, and we've seen a huge array of application areas develop over the past few years. So we're really zooming in on IEC 61850 based protection today. But if you are interested in any of these other areas, I encourage you to submit a question or please contact us by email or check out our website for more information. All right. At this point, I'd like to pass things over to Eric, who will present for about 15 minutes, and then we'll go into the demo.
Okay, good morning, good afternoon, and good evening to everyone. Welcome to this webinar. Thanks, Katie, for the introduction. I'm Eric Xu from RTDS Technologies. The topic today is on hardware in loop testing of modern power protection systems using IEC 61850. As we know, IEC 61850 is an international standard defining communication protocols for power utility automation. It has been widely adopted in modern substations of electrical power systems. For simulating power systems involving physical protection and control devices that require such communication for data exchange, interface that supports such communication is a must for the simulator. In this webinar, we will have a quick overview of the closed loop protection. Okay. We'll have a quick overview of closed loop protection testing using RTDS and a detailed look at the hardware and software features for such applications. We'll run a demo using a protective relay that supports both goose and sample values for a line distance protection scenario, followed by the Q&A session. Without further ado, let's get started. Testing protection and control devices are generally divided into two categories: open loop testing and closed loop testing. Compared to the open loop testing, the closed loop testing has the advantage of providing the complete interactions between the device under test and the simulated power system. It is the ideal approach to fully study a target power system involving single or multiple physical protection and control devices, and to better validate the protection control functions of the protection control devices in the integrated environment. Now, to achieve such a closed loop testing, a real-time simulator that is capable to provide realistic power system signals and support required communication protocols is needed. In RTDS, we provide two solutions in terms of the interface between the simulated power system and the device under test. One is referred as the electrical interface, and the other one is the IEC 61850 interface. As a simple example shown here, we have the power system simulating the RTDS, okay, in this gray box. Two protective relays are used to protect the breaker at each end of the line. If the devices do not support IEC 61850 or not required for the specific application, the conventional I/O cards of RTDS will be used for data transmission. The analog output card will be used to send the secondary side voltages and currents of the corresponding breaker from the simulation to, in most cases, the external amplifiers, then to the physical input contacts of the relays. Digital I/O cards will be used to send the breaker status to the relays and at the same time receive control signals, such as trip and rate close signals that send from the relays back to RTDS to operate the breakers in simulation. Now, if the device under test supports IEC 61850 and the focus is to use it for the specific application, then the IEC 6150 interface may be applied. As shown in this slide, we have the same power system simulating RTDS. For data transmission, instead of using the conventional I/O cards, the network communication card, the GTNet or GTNet X2 is used. And the GTNet card is the older generation and the GTNet X2 is the current generation. From here, I will use the term GTNet to refer both GTNet and GTNet X2, unless the differences between the two needed to be addressed. Now here, GTNet SV is used to send the voltages and currents, most of the time the primary side values in the form of IEC 6150 sample values protocol to the external relays through an Ethernet switch. In a similar manner, breaker status from the simulation, trip and rate close signals from the external relays are exchanged using the GTNet GSE in the format of IEC 6150 Goose protocol. Now let's have a detailed look of the current generation of this network communication card. The GTNet X2 card is an interface between the simulation and the external devices using known communication protocols. It has 2 GTNet modules. Each module on the GTNet X2 is independent with no shared resources. It works just as 2 individual GTNets. It supports SFP modules for Ethernet and runs 5 to 10 times faster than the previous generation. It also supports multiple IP addresses for limited protocols. A typical connection of the GTNet X2 is shown here. A module on a GTNet X2 is connected to the NOA core or PB5 or GPC through a fiber. The data exchange between the GTNet X2 and the external devices down through the Ethernet interface, which may be either in fiber or copper based on specific requirements. Next, let's have a look at the protocols that support it. Firstly is the GSE and SV protocols for IEC 61850 GooseIn sample value applications, which will be the focus of this webinar. There's a DMP protocol for DMP3 applications and 104 for IEC 70-5-104 applications, followed by the PMU protocol for IEEE 37118 applications. We also have a protocol named SKT, which comes with the purchase of the GTNet X2 card and free to install on the GTNet for more generic TCP UDP socket applications. Continued by a protocol named Playback for replaying large capture wave data. Last but not least is the Modbus protocol for Modbus communication over TCP IP. So next, let's have a better look of the GSE and SV models. There are 3 GTNet GSE components available in the protection and automation library, V2, V5, and V6. We'll just highlight V5 and V6 today. V5 component supports edition 1 of the standard and logic node GGIO for outgoing Goose dataset. It can publish and subscribe up to 256 points of data types in either Boolean, integer 32, float 32, or double bit precision. If quality information is required, then the number of points supported is folded to half. Up to 4 Goose messages may be published, and up to 16 Goose messages may be subscribed. V6 component supports edition 2 of the standard. And besides GGIO, V6 supports logic node XCBR and XSWI for outgoing Goose dataset. Starting from version 6, IEC 61850 server with limited functions is supported using the GTNet X2's IP address. Another new feature is the routable Goose. Now, due to the limited time, these 2 new features will now be focused in today's demo. Just a little more touch on the server feature. When a simulation case involving GSE version 6 is running, the GTNet X2 module acts as a IEC 61850 server. A connected client may perform some of the functions as listed here, such as reading breaker status, enable, disable Goose control block, send CSWI control command to operate a breaker, and more. Now let's move on to the sample values. There are 3 GTNet SV components available in the protection and automation library, which are V5, a special edition, and a V6. We'll just highlight the V5 and the V6 today. Now, V5 component supports edition 1 of the standard. It works either as a publisher or a subscriber. So only one mode is inactive at a given time. It supports sample rates of 80 or 256 samples per cycle. Like the GSE version 6, SVV6 component supports edition 2 server and routable sample values. Compared to SVV5 component, more sample rates are supported in version 6, as shown in this table. Depending on the selected sample rates, up to 24 data channels may be included in the published or subscribed SV stream. Now, besides the GTNet family, we have another hardware that supports sample value protocol, which is the GT FPGA SV. The application was developed on the Z-Link's Vertex 7 FPGA evaluation kit. Some of you may notice that this unit is also used for MMC-related applications of RTDS. Depending on the firmware installed, the unit would function accordingly. As shown in the picture, the first difference we can see between the GTNet X2 and the GT FPGA unit is that there are 16 Ethernet ports available on the front panel of the GT FPGA unit. Whereas for GTNet X2, there are only 2 ports, one for each independent running GTNet module. So no surprise, due to the extra ports, the GT FPGA SV can publish and subscribe up to 16 streams simultaneously. Remember that on a GTNet X2 SV module, it works one mode only at a given time. The GT FPGA SV also supports a substep mode, which is for applications required for even higher sample rates, such as 96K and 250 kilohertz. The IEC 61850 server and the routable features are only available on the GTNet X2 though. Okay, before heading for the demo, let's have a quick overview for the TWRT related applications. Firstly, TWRT means traveling wave relay testing. One of the key advantages of traveling wave-based protection over a traditional phaser-based protection is the fast tripping, which in turn improves transient stability and the safety of power systems. Traveling wave-based protection scheme investigates the current and voltage waves that are generated by a fault. Commercially available traveling wave relays normally have the sampling frequency in the range of 1 megahertz. To evaluate and verify the performance of traveling wave relays, a testing platform that can provide traveling wave phenomena with sufficient accuracy and time resolution in a closed loop scenario is highly desired. RTDS provides 2 real-time simulation solutions for traveling wave relay testing. One is based on the FPGA unit, which is referred as FPGA-based TWRT. The other is based on the NOAA core, which is referred as NOAA core-based TWRT. The FPGA TWRT solution is for small-size system that may have up to 4 line segments. The whole power system is simulated on the FPGA hardware with a fixed time step of 1.54 microsecond. The NOAA core-based TWRT solution is capable of simulating larger system representations with a time step of around 2 to 3.5 microsecond, depending on the complexity of the system. Both solutions provide the frequency-dependent phase domain transmission line model, which has been proven to be more accurate to represent the T lines for TWRT applications. So far, RTDS is the only real-time simulator that provides the frequency-dependent phase domain transmission line model and has been adopted by traveling wave relay vendors such as Schweitzer Engineering Laboratories for traveling wave relay testing. Okay, that brings us to the end of the presentation. Let's move on to the demonstration of closed loop relay testing using IEC 61850. Okay, so here is the simple network for the demonstration. Which contains a double circuit transmission line with a generator and an infinite source at each end of the two buses. There are 4 breakers, okay, at each end of the terminal. The one at the right top corner here is randomly selected to be protected by an external relay, which in this demo is a ICL 421 transmission line protective relay. The other 3 breakers are protected by using the distance protection relay component that can be found in the protection and automation library. The relay components in the protection and automation library were developed based on generic protection functions. They may be used when physical relays are not accessible. So the top line is the focus for the demo, and we would like to apply faults along the line so that we may observe and validate the response from the physical relays. To apply a fault along a transmission line, a feature called draft variable is used. The idea is to model the target line using 2 lines here, with the length added up together to be the whole length, so that a fault bus can be placed in between. This is achieved by configuring 2 parameters in the T-line calculation blocks of the 2 lines. So let's open these 2 T-line calculation blocks. So here are the 2 parameters, similar here. In this case, a draft variable named fPoint of unit in percentage is linked to a draft variable slider with the same name, which is here. Now this fPoint slider then can be used later in runtime to set the length for the left side T line in percentage of the original length. Then the right side T line would have the rest of the length. By doing that, we can move the fault location along the line. More details may be found in tutorial chapter 7 if needed. Here are the fault branches. So if we view the diagram in 3 phase, we can see that these are the line to ground faults and these are the line to line faults. Here it shows a typical fault logic. It includes point on wave control here, fault duration, fault types, and a fault location in terms of either internal or external faults. Now for this demo, we will focus on the internal faults on the top line. The hardware used in this demo includes a Nova Core chassis with at least 1 core license. So this case basically could be run with just 1 core only. And we also need a GTNet X2 card, which one module running SV protocol and the other module running the GSE protocol. And we will need a GTSync card. Okay, we'll have a look at the hardware later before running the simulation. So now let's have a look at the IEC 61850 interface that will be used for communicating with the physical relays. Let's start with the the SV component. Now, the main function of the GTNet SV in this demo is to send voltages and currents at breaker 2, which is here, to the external relay using IEC 61850 sample value protocol. The key parameters associated with the IEC 61850 SV protocol, such as the SV ID, the destination MAC address, and more are configured in this menu tab. The variables representing the voltages and currents at breaker 2 are entered in this name and format menu tab here. As you can see, for example, the channel 1 current is from the breaker 2 A phase current here. Okay. So similarly down for the other phases, and the voltages are from this bus here. Now let's have a look at this GTSync component here. Most of the time for sample value related applications, the publisher and the subscriber need to be time synchronized. In RTDS, we have a hardware called GTSync. that developed for use in the situations where the synchronization between the simulator and the external devices is required. Let's move on to the Goose interface here. This is the GTNet GSE component. The main function of the GTNet GSE in this demo is to send breaker status to the external relay and receive trip and reclose control signals from the external relay using the IEC 61850 Goose protocol. Now, the simple logic here is to get the parameters that needed to be sent to the relay, which include a 3-bit integer STBRK2, which comes from this breaker control component, representing the phase ABC status of breaker 2. And there's a 1-bit extra status from the relay model at the left side terminal, which is here, CS12, CS12, which representing a permissive transfer trip signal for the POTT scheme adopted in this demo. The combined output variable TX2B, which contains 4-bit information, later will be associated with the GTNet Goose output dataset. To configure the GTNet Goose, embedded tool called SCD Editor is used, which is accessed by right-clicking on top of the GSE component and go edit, and then select this SCD file from template. Here, I will just open and then review the configuration of this demo case by selecting the option above. From the, in this demo, an output data set which contains multiple Boolean data attributes is created here. From the information I mentioned earlier, we would need 4 Boolean data attributes in this data set to be associated with the output variable TX2B. And you see there are 8 of the Boolean attributes here. Now the other 4 in the data set are just there for debugging purpose, so you can ignore them for now. Now the Goose communication parameters, such as data set name, Goose control block name, the destination MAC address for this created output data set are configured inside of this edit IED window. We'll come back to the GS input, the Goose input configuration later. Okay. Now let's see how the output variable TX2B is associated with the output data set that was created. So here we're in the output signal name types menu tab. After the data set is created in the SCD editor, the type of each enabled data attribute is automatically detected as here. So they are all Booleans. As you can see here, bit 1 to 4 of output variable TX2B are mapped to the Boolean data attribute 1 to 4. Okay. Which is expected. Again, ignore the other 4 outputs for this demo. For GTNet Goose input configuration, we need to go back to this editor. Firstly, we need to import the configuration file that containing the Goose output information of the external relay. Later, we will touch on the process how such a file is generated in the relay's configuration tool. For now, assuming that we have the file ready, the file can be imported by going through File, Import. Then select the target file. In this demo, it is this SELCID file. Once the file is imported, as I did already, the relay's Goose output data set would be shown below the GTNet IED, okay, under the IED section here. As we discussed earlier, we expect the relay to send the trip and rate close signals In this demo, the relay was configured to send a goose message with a dataset containing this required information. Here, the Boolean attribute 1 to 5 are representing A phase trip, B phase trip, C phase trip, reclose, and the permissive transfer trip, respectively. Again, ignore the rest. Okay. Now, to associate these 5 data attributes from the relay to the GTNet Goose input, we can drag each one and drop it to a field here that corresponding to a specific input. For example, you can just easily do like this. Here we have the top 5 mapped to the GTNet inputs 1 to 5, as shown here. Okay. Next step is to see how the GTNet inputs are associated with a variable input in draft, and then to control the breaker. Here we're in the input signal name menu tab. In this case, a integer, a variable named GooseIn, okay, is given to represent the Boolean input 1 to 32. Next step is to use this variable GooseIn to control breaker 2. To do that, the variable GooseIn is given to the 2 inputs of the breaker control component to eventually operate the target breaker. As seen in this menu tab, bit 1 in variable GooseIn is now associated with A phase trip. Similarly down for B and C phase. And then bit 4 in GooseIn is used, okay, is used to reclose any opened phases. Now ignore this 3-phase trip input since it's not configured in the relay. The output variable CB2 here is then used as a control word to control breaker 2. Here we can see that bit 1 of CB2 controls A phase, and then bit 2 for B phase, and bit 3 for C phase. Okay, so next let's have a quick look on the relay settings. There are 2 software from the vendor need to be used for configuring the relay for IEC 61850 applications. The QuickSet is one of them. In this demo, this tool is used to set the line parameters, CT-PT ratios. Okay. Now the length of the protected line is 97 kilometers here. Okay. By the way, the line impedance data can be obtained from draft by viewing a file called map file after the draft is successfully compiled. Okay. So we can go here and view map file. Be careful that since 2 lines are used to model the protected line, so in our case, okay, we have this TL1A and the TL1B together to model the whole line. The impedance of TL1A and TL1B need to be added up together to get the impedance of the protected line. Okay. Now, in QuickSet, it also used to set the protection elements. In this demo, the zone 1 is set to 80% and the zone 2 is set 120%. It's also used to associate breaker status with relay goose inputs, which is down here. And it's used to set the sample values reception as well, which is down here. So this MAC address needs to be matched with the GTNet SV multicasting addresses as we enter here, right? 040188. Okay. So that way the relay will be able to subscribe the sample value messages that published by the GTNet. The next software is the architect where to configure the Goose inputs and outputs of the relay. Here's the architect project for this demo. So firstly, the GTNet Goose configuration is imported into the architect here using the SCD file that's saved from the SCD Editor. Okay. Then the GTNet outputs. The GTNet output data set here, the GTNet outputs are mapped to the relay's Goose inputs. So these are the GTNet outputs, and these are the the relay's Goose inputs. Then the GTNet outputs. So the next step is a Goose data set. Okay. Output data set here named TWRT, which contains the required control signals was created. For example, you can see the trip signals here, and there's a reclose, and there's a permissive trip here as well. Right after a Goose control block, and associated communication parameters are created in this Goose transmit tab. So at the last, you need to export this configuration file. So it will be used in the GTNet SCD Editor to associate with the GTNet inputs. Okay. And the last step is to send the settings to the relay. Okay, so before running the simulation, let's have a quick peek of the hardware used. So this is the Nova Core cubicle, and we're using the top chassis here. Okay, and we have a GTNet chassis here as well, which can hold up to 3 GTNet cards or X2 cards. But in this case, we're only using one card here for this demo. One module is running Goose. The other module is running the sample values. Now, this is the relay we're using. On the back of the relay, there are only 3 cables here, besides the power cable. 2 of them are the Ethernet cables. One for the station bus communications, and the other one is for the process bus communications. We also have a BNC cable connected to the relay, which actually provided by the GT Sync. So the GT Sync works as a master clock in this demo. They're providing the IRAB signal to the physical relay. So let's move on to the runtime. Once the simulation is started, you may verify the Goose and the sample value messages that are sent out from either GTNet or the relay in Wireshark. Okay. For example, I have the Wireshark open here. I can just type in a filter Goose and then do a quick capture here. Okay, let's stop here, and let's double check the destination MAC addresses for the GTNet and also for the relay, right? So this is the one of the focus, right? So the GTNet sends the Goose messages to the address of 010188, okay? And the SEL, the relay is sending the Goose to 0101B8. Okay, so if we back to the Wireshark and okay, find the 010188, so that's from the GTNet. Okay, let's do a filter here. Now we can do a quick check, but just go over some of the parameters here, so you can find your data set, okay, that matches your configuration, and the Goose ID, okay, and also there are 8 items, even though we're only using 4, but the data set contains 8 items there, and because we're sending the top 3 are corresponding to the status of the breaker, so they should be all on right now at the steady state. So that's is confirmed, right? And there's no trip, so there's no permissive trip either. Okay. And also you can probably like verify your sample values. Okay. If we go back to the our configuration here, we know that GTNet is configured to send the SV packets to 040188. Okay. Now back to the Wireshark. After entering the SV as a filter, we have this 040188 here. Okay. Now we can see this is our message, right? We have the same the SV ID that configured in the GTNet, and there should be 8 data entries here, right? 4 for currents and 4 for voltages. Now be careful; these are instantaneous values, okay? And the resolution here, based on the standard, the current is 1 milliamp, and for voltage is 10 millivolts. Okay, that's why you see a bigger number here, and they're all integers. Okay, before applying any faults, let's compare the relay readings with the values in runtime in steady states. So this is the breaker 2 that is being protected by the physical relay, and this is the line currents that we're sending out to the relay through SV protocol, which is in kiloamps. So it's 190 amps, and then the voltage we're sending out is this one here in their phase values. Okay, 288.7 kilovolts. Okay, so one way to verify this is to have a look of the front panel of the relay. Okay, so probably you can see the values that are read by the relay. Okay, the voltage is 288.5 kilovolts. Current is 189 point something. Okay, the other option is to use this embedded HIL terminal. Okay. So let's just meter the, so we get a capture from the relay, okay? So we can compare this with the runtime values that we're sending, okay? 189, that's the current, and 288.7, okay? Now, depending on the CTPT ratios, how accurately you enter the ratios, this may vary a little bit, okay? All right, so now we are ready to apply some faults. For now, the add point slider, the drop variable slider, is set to 75%, which means the fault location is at 75% of the original length from the left terminal. Okay. Now, since the relay is at the right side terminal, so it means that the fault location is at 25% of the original length from the relay side, which, by considering the length is 97 kilometers, the fault location should be at 24.25 kilometers. Okay, and we're about to apply, say, A phase to ground fault. So we expect to observe that this bit here, which represents A phase, will be open and then reclosed. So this light will be turned off and turned on back again. So it will change to green to represent an open state, and back to red to represent a closed state again. Okay, so after I click the fault, we should hear a click from the relay as well, and see the we can observe the changes here, and also we can see the incoming Goose messages status, and we can compare that with the relay as well. Okay. Okay, so that's expected. So A phase was open and then reclosed, and we can have the interested parameters monitored in runtime here as well. So we can see the A phase, that's the primary side A phase current. And from the breaker status here, we can tell, okay, the breaker 2 A phase is open and then reclosed. Okay. From the coming Goose messages, okay, we know that the first bit is A phase trip, so that's correct. And then the reclose comes in here, and this is that permissive trip here. Okay. Ignore the other three. These are for debugging. Okay. Now let's compare the. Let's have a look at the result from the relay. Okay. So you probably can see the results from the front panel of the relay, but it also the hyperterminal also updated the result here as well. So the event is detected as AG trip, which means it's A phase to ground trip, and location is 24.36. Remembering the ideal location is 24.25. Okay, and this tells us like the relay is synchronized to a high resolution IRIC, okay, which comes from the GTSync card. Okay, so it's a zone 1 A phase to ground fault. Okay, and then you have the pre-fault measurements here, and also this is the measurements for the at the fault. Okay, so let's try one more scenario. Let's move the fault a little bit further away from the relay. So 15%. So whenever we need to change the draft variables, we need to stop the simulation. Okay, the draft need to be recompiled. So you can just click the option there, and it will automatically recompile the case and then immediately rerun the case. Okay, let's do an update here. So when we set to 15%, it means that the fault location is at 85% from the relay side, right? So remember that we set zone 1 of the relay to be 80%. So this is outside of zone 1, so it's a zone 2, right? And then let's do a different fault, BC to ground. Let's try that. Okay, let's clear the target here. Have a fresh view here. So the relay back to normal, reset already. So what we expect the relay to operate is all 3 phases will be opened and then reclosed. Okay. All right. Now check out our simulation here. So we can see now the fault. This is A ground. This is B ground, C ground. So we can see this is a BC ground fault, right? So that's correct. And then from the status of the rigger, all 3 phases are opened. We're opened and then reclosed here. This is the goose input. Okay, the relay sent the trip for all 3 phases, A, B, C, and then this is the reclose, and this is the permissive. Okay, let's verify that in the relay side. Okay, so the event is the BCGT. So BC phase to ground, and the location is at 84.13. The ideal number should be 82.45. Okay, and we have the target is BC phase to ground. Okay, that's a zone 2. So and then similarly you have all the values for pre-fault and during a fault. Okay. Okay, I think that brings us to the end of the demonstration.